Welcome to MOOC course on Introduction to Proteogenomics. In today's lecture, Dr. David Fenio will talk about training a model and test model. It will be continuation from the previous lecture, where Dr. David Fenio will briefly discuss testing error and training set size, where he will also discuss about low variance and high variance. He will provide a detailed idea about regularization and how regularization helps in training a model. He will then talk about how to divide data set between training and test and how to deal with situation where the data set is small in number. I hope some of these discussions and points will be very important for you to consider when you are planning a big clinical study for your own project. So, let us welcome Dr. David Fenio for today's lecture.
So, another way to say this is that if you have a data set, you should divide it into test and training set. Now, the problem for us again, which is always the case, that we don't have very much data. So, if we separate out a large chunk into the test set, we don't have much left for training. And that's not good, because I mean, as we said before, the larger your training data set, the better you will do, the better the model. So now we're going to come back to this, but what people do is cross-validation, where they do this separation one way and then do the separation another way and so on. But we'll get back to that a little bit later. So now if we separate out the training set, so we saw now this is the same data, but the y-axis is on a log scale. So we saw that the training error can go down. We can, by making the model complex, we can make it go to 0. But if we then compare it to our test set, that's, the test error goes up as we make it make our model more complex. So one way to get around that is if we really have a lot of data. That helps. So in this case, now we're looking at the test error as a function of training data set. And as you see, sorry, the y-axis is not labeled, but as we increase, so the numbers there that are shown are the number of points that we have. So you see that when we have few points like 10, we just increase our complexity, model complexity a little bit, the test error. But if we have large number of samples, so the other two curves that are not labeled, which have low errors, are 1,000 and 3,000 points. So that's one way so the best way actually of doing what we'll talk about later, which is regularization, to get around this problem, is to have just a very large data set. So I'm going to just skip this. Okay, so now let's say we don't have, now so far we've had linear data. So now we're going to have a little bit more complex data set, and we're going to do the same analysis. So here, now, it's good to increase the complexity a little bit, because our data, I mean, as you can see, we can't fit that function well with the line. There is no way that we can get a good approximation. And that's why we see that if we have a first-degree polynomial, which is a line, we don't, and both 1 and 2 gives us very high errors. But then it goes down, but as also before in the example, when we continue increasing the complexity, the training error goes down and down. And eventually, it's very low. But then at some point, the testing error goes up. So that's why we should choose the complexity somewhere here close to the minimum. And it's usually better to be more conservative, so I mean probably better not to choose 5 or 6, but rather 3 or 4 in this case. That's sort of a rule of thumb that since we have this flat region, it's better to be more conservative. Yeah.
So can I ask a quick question? So it's like counterintuitive. When your training error is going down with increasing polynomial or number of variables, why should the testing error go up? Because you are, I mean, training it well, but when you're testing it, the error goes up.
Oh yeah, so I mean the reason is that you overtrain it, so you overfit your model, so you train it to the particular noise that's in your training set. So it learns something that's not relevant to the process, but just because you have a finite set that you're training on, that will have some, by chance, some noise. And that's what you learn, that noise, but that doesn't generalize.
How to determine when the training is complete, like we are not going to overfit the training results and the testing area is going to again rise? Like at what limit, how will we end up like the training?
Yeah, so
we are going to say that this is not going to be overfitting again.
Yeah, so we'll talk a little bit about that. I mean, overfitting is always a worry, even if you take these into account. But the way we're going to talk about that, and usually we do it through cross-validation. But we'll get back to that later. And this, I'm going to skip this. So now, regularization. So again, Mani mentioned this. So what a little bit formal way that we're going to look at. So I don't know how familiar you guys are with mathematical notations, but this is sort of what we do. One way of describing what we do when we train a model. So we have W are our parameters. So W here is bold. So meaning that it's a vector. So we have many values of the parameters, so W1, W2, and so on. And then we have a function, L, which we call a loss function. And in the case of linear regression, we mentioned that it's the sum of the square deviations that are a good loss function. But it's not necessarily the only one. There are other ones also. You could also, you don't need to take the square. You could have the absolute, add up the absolute values. So we choose some kind of loss function. And actually, the L should not be bold. Sorry about that. Because it's a function with one, it has many vector as an input, but the output is just, and then we try to find the W which minimizes the loss function. So that's why we call it least squares fit. So that's what we are doing. But again, so we saw that if we do this, and have many large vectors, so many W's, we run the risk of overfitting. So what we can do is add an extra sum here, where this is some kind of function of the absolute value of W. So meaning that we are going to force W to be pretty small. And then this parameter lambda is the one that governs that. And there are two that are pretty often used. Is either you add in the square of the length of W, or you can, and that's called ridge regression, or you add in just absolute, the length of W. So those are two ways to regularize and minimize the risk of overfitting. But again, remember that even if we do all these things that we're going to talk about more things, that to try not to overfit, even if we do this, there is a risk that we overfit. And we should always be worried about overfitting. So let's have a look at what happens here. So now these are just 10 points here. Again, we do a linear regression, but with a polynomial of degree 9. And it will be a widely oscillating curve that is cut off over here. And we see that the coefficients these are the, for the linear case, it would be these two that would give us a line. But then we see that the other coefficients are very high. Now, as I mentioned, the best way to regularize is to have lots of data. And if we have, instead of 10 points, 10 measurements, 100 measurements, we see that we get reasonably good fit, a little bit wiggle, and we see that it's mainly dominated by the two first ones, which would be a line. And if we get even more data, it looks even better. But outside the region, of course, anything can happen, where we don't have any data. So now if we look at the same thing, we add some regularization. And so we instead of just minimizing the loss function, we minimize the loss function plus a lambda times in this case, I believe it was the square of the parameters. So then the same thing, actually, here is the inset. So this is what we looked at previously without regularization. Those are the insets. And we see that with regularization, we see that we get a much better fit, and it's dominated by the two first parameters in all the cases. So that's, we definitely need to do that.
So inset one is regularized one, you are saying?
No, the large, this is the regularized one, and this is the same as the unregularized, that's the same as the previous slide. So if you look at this, and I go back to the previous, so this one is the same as the inset in the next one. Okay, so then another way of doing it, which is to do nearest neighbor regression. So in this case, we want to see what these red points are the ones we're interested in. So for example, if we take the 3 nearest neighbors, we would take an average of these values and approximate where the red ones would be. So that's the linear regression. We have a very sort of fixed model, but here it's really, we're just looking for data points that are similar. So it can become very flexible, but often with high dimensions, there are no points that are similar, because it's, I don't know, you should try to think about how a very high dimensional space looks like. And it's not easy to think about. So try to think about, instead of, in this case, we have 2 dimensions, just 100 dimensions. So in 2 dimensions, you often have points that are reasonably close, not so much in this case, but in 100 even, you spread out all your points in a much bigger space, and it becomes like nothing is near anything else if you don't have an enormous amount of data, which we usually don't have. It's often, even if a linear model is not we know that, let's say, the linear model is not right, it's often still better to assume a linear model because in most of our cases we don't have that much data. So that's another thing. Okay, so we looked at a little bit about model complexity now. Now I will switch to how do we train the model. So we already mentioned that we define a loss function which gives us a energy landscape that we try to find minima. So, and usually we have our function defined, and then most often we start at a random place. Let's say here we just, at first we just randomly assign our parameters, and then what we want to do is to go from our randomly assigned space to the minimum. But we don't, I mean, and also we have this 10,000 dimensional space that we have to walk around in. And so but what we know is the local environment. So what we can calculate is if we are here, we can see what the slope is. In which direction should we go to at least get further down? And so we calculate the derivative locally, and then we take a small step in the direction of down. And so then maybe we go there, then we repeat this, take another step, go even further down, and then continue again. But now what can happen when we get closer to minima is that we take too big of a step. So we over jump, and we're going to see that it's often good to start taking big steps and then at the end take smaller and smaller steps. Another problem that we can run into is that if we start in a region where it's very flat, there's no gradient almost, or maybe not at all, and then we end up stuck there. Since we always want to take a step in the direction of the gradient, and the size of the step is also proportional to the gradient, so then that's a problem. Another thing that can happen is that when we get stuck in minima. Those are, I think, the main problems that we run into. Okay, so let's look at how this error landscape looks for linear regression. Now, as you probably remember from undergrad, for linear regression we don't need to do gradient descent because we can actually solve this analytically. But we're still gonna, since it's such a simple case, I still wanted to walk you through how it looks if we would need to do gradient descent with linear regression. So again, so we have a few points. Here now we have the slope of this and the intercept. So if you just look at the slope, if we change the slope from this is the optimal position, this is where we have the minimum, that's the line shown, it will, the energy, the sum of the square errors will increase. And we can look at this in different ways. So this is the three-dimensional, if we look both at slope and intercept, and that rotated. We can look at it from above, where we have two dimensions. Intercept is here, slope is here, that's the optimal place where we have the best solution for the linear regression. And we can look at it like this, like a map showing the minimum here and the gradient. If we have two different lines, the same number of points here and same number of variation, we get slight variation in how this energy landscape looks like. But if we have really a lot of points, the energy landscape is well defined with nice concentric circles, which of course is helpful. So we mentioned that it's actually, we don't need to use the sum of the square errors, we can also use sum of absolute errors. The energy surface becomes a little bit more jagged and not as round, but it's also a possibility. And especially when we have outliers, that could be a better solution. Another thing, if we have very little variation, so that lots of points that define the line well, we get a very sharp minimum. But when we have more error, we get a much more, much less well-defined minimum. Okay, so let's go through a case now. We're going to walk down this surface. So we randomly start here. So this is again intercept and slope. So we have our data here. This is our randomly assigned line. You see that it's not great, but it's also because we are pretty far away from the optimal solution. So now we're going to take a small step in the direction downhill at the gradient. The gradient is perpendicular to these height lines. The first step we take would be going perpendicular here, and depending on what we choose the step size to be, we'll take a small step here. Then we take another step. Now, because of the curvature changes, we're going to curve in, and then we continue going down, following the gradient. And eventually, and on the side there, you see that now when we reach close to the middle, the line fits very well. And we can randomly start from different places, and we end up in the same location. Because with the linear, this is a very nice surface. Some threshold here that gives us a lot of true positives and very few false positives. But in another case, if we have these much closer to each other, we can't do that distinction, but we can still use this to select where to set our threshold. And then we can see what happens if there is an uneven distribution. So the other thing we can do is, if we have the false positive rate and a true positive rate, we can create what's called the receiver operator characteristic, an ROC curve. So how many of you have made ROC curves? So that's a very common way to evaluate classification. And then when we do comparisons, one thing that in this case, we have good separation. So the ROC curve will start down here and go almost up to the corner here. So we have that the true positives are separated from the false positives. And we can use for example, the area under this curve as a characteristic of how well we're doing. And so if we have completely random distribution, they would be completely overlapping, we would just have a line along the diagonal. And then these are just for the other case where we have them much closer. You see that here the ROC curve is much closer to the diagonal. And these are just cases for the other. Okay, so one of the probably conceptually easiest methods is the nearest neighbor. So here what we do is we just see where what's the nearest neighbor, what class is it in. And of course, if you do evaluate this on the training set, you're going to get that the error is 0, because it's here is one example of where it's definitely it shows that why one shouldn't use the training set to validate. So here now we have the two groups, and if we use one nearest neighbor, we get a good separation between them. But in another case, if we take the nearest neighbors when they're more intermingled, we see that we get a very complex decision surface, and no one would claim that this is really what it is like. So this is a very clear case of overfitting. So now we can, of course, average over a few nearest neighbors, so in this case 2 nearest neighbors. Now it gets a little bit more plausible, but for example, there's still an island here in the middle of the blue. So then, and it gets, as we go to more and more nearest neighbors, the decision surface becomes more plausible. But again, with nearest neighbors, the problem is often that when we have many dimensions, it's just there is nothing that's really near to anything else. Okay, so now a method that often we can start with to just evaluate is logistic regression. If you remember, it looks very similar to linear regression, that we have the input, our different protein measurements. We have our parameters, the weights for each. We multiply each value with its weight, add them up, and add a constant. But now so far that's linear regression. But now in logistic regression, that becomes the parameter of a function, of the logistic function, and which we call sigma, and it looks like this. So we introduce a non-linearity, and as we see here, so these are 4 different parameters of we get this transition from 0 to 1, but depending on the parameters, we have different sharpness. But what so now we want to have classification, so we have 2 cases. So in the extremes here, at low values, we have that the output is 0, and at high it's 1, and then we have this transition region. So that's why we can use the logistic function for classification. And this now is just comparing them. So linear regression, this is with one x value. So we have the slope and intercept, that's linear regression, and then logistic regression, we just have the same expression, but we have a nonlinearity. The other thing that we looked at the shape of this function going from 0 to 1, and since we're going to do a gradient descent, we need to look at its derivative. And there is actually a very simple expression for its derivative, and it looks like this. So again, it's very flat out here when we are far away from the transition. The derivative is 0, and if you remember, for gradient descent, that's not very good, because if the gradient is close to 0, we get stuck there. So we want to make sure that we're not too far away when we start. Otherwise, we won't find it. So this is just an example of where we done logistic regression. And if you remember, from the nearest neighbor is the same data set, we got pretty close to a straight line there also, and that's what we get in this logistic regression. So now, if we look at the energy surface of this, so remember that for linear regression, when we use the sum of square errors, it behaved really nicely, but here we see something completely different. It's really not, doesn't behave well when we use the sum of square errors. And it's probably easier to look at it here. So this is our minimum in there, So we have a huge mountain behind it, very steep gradients and very shallow gradients. So we have to in some way find our way in here through very shallow gradients. So what this means, this is a bad choice of a loss function. And this is just some other ways to look at it. We again have that if we approach from here to the minimum, it's very shallow, but then it's sharp. And then here we have, looking at the other way, we have this plateau where we can also get stuck. Now, this is, you don't need to remember this, but there is an appropriate loss function for logistic regression, and that's this one, but I'm not going to go into detail. So then, when we apply that loss function, the surface become much more manageable, and we can do gradients. We still have that it's in one direction it's more shallow and sharp in the other direction, so it's not as nice of a surface as for linear regression, but it's still reasonably good. And also the other thing that for logistic regression, we don't have an analytical solution. So here we have to do gradient descent. Then if we have the same number of points, same distribution, so this is one class up here at 1, and then the other class at 0, we see that the surface varies a little bit. If we have fewer points, we get quite much larger variations in this case, and when we can also do gradient descent through this. So we start out here, and then we walk down. But again, we have to be careful that we don't take too large steps when we come close to this very sharp, steep hill, because then we end up being thrown far away from the minimum. So again, so for both logistic and linear regression, we have these hyperparameters. We have to decide on the learning rate, how we schedule the learning rate, usually how we decrease it, and if we want to remember some of the momentum and have some friction built in. So if we look at regularization here, again, we want to guard against overfitting, but so here in this case, so the same as for linear regression, we can also add in polynomial terms. We can do the same thing. I mean, I saw the expression was the same, so for logistic regression, we can do exactly the same thing. So here we have, there's no linear surface that can separate the yellow and the black here. If we have, so if we add in higher degrees of polynomials, we can do a better separation. But again, in this case, our surface is a little bit too jagged, and it's probably overfitting. But then we can fix that by doing the same type of regularization, either lasso or ridge regression. So, and how does that, if we look at the energy surface for logistic regression, with no regularization, we had this case, and when we add in regularization, it actually helps us also in the speed of learning. That meaning that, and you see that the gradient here is, when we add in the regularization, is much higher, so that it's more comparable to this. So we will be able to find the minimum faster. So then a few examples of, so we had, so you probably heard about neural networks and deep learning. So what that is, so each of these nodes here is a very similar node to one logistic regression unit. So we have the inputs, the different protein measurements, we have the weights, and we multiply each weight with each protein measurement and sum them up, and then we have an offset. And we have some kind of nonlinear function, which can be a logistic function, but it can also be other things. And here we have, we always have one input layer, at least one hidden layer, and an output layer. And this illustrates what's called the fully connected network, where each node in each layer is connected to all the nodes in the next layer. And now this only shows one hidden layer, but nowadays it's very popular to have many hidden layers, and that's why it's called deep learning, because you have many layers. And right now this is the most popular method that people use, but it does often require, if you don't want to make a very small neural network, but at least for these large ones that people do, you need a lot of data. And in most cases in proteogenomics, we don't have enough data to build neural networks. So most recommendation is, even there's all this hype of deep learning, but best to not, for proteogenomics, not to get into that, and unless you have a very good reason. And probably 10 years ago, support vector machines were what everyone did, and it was a very popular, I mean, I would say probably support vector machine 10 years ago was what neural networks are now. So there's always fashion in which methods are but support vector machines are very useful, and so what they do is they, of course, find a plane that separates the data, but then they also try to find the largest margin. And the support vectors are the data points that are on these margins. I think Mani showed this slide on tree-based methods, and those are also very powerful methods that, especially in this case, showing that you can have a very highly non-linear function that you can classify all these, even though they're quite intermingled. So each of the nodes in the tree is a decision whether it's some measurement is larger than some or smaller than something. You can go in different directions. So I would say that right now the most success people have is with either support vector machines or tree-based methods, but actually I would recommend starting with a simple method like logistic regression first also, and include those. And there's a theorem that's called the no free lunch theorem, and this was in the 90s. Some people showed that when you start with a new project, you have a new data set that you don't have experience with, there's no way to tell which method will work best. So it's really sometimes a tree-based method like random forest will work best, sometimes logistic regression, sometimes support vector machines. So it's really, and of course all the methods have lots of parameters that need to be adjusted. So what people often do is they try all possible methods. Now, of course, what you can't do is to train one method on your training data set, test it on the test data set, train another method on your training, test it also, and do this many times for all the, both for the different methods and for the different hyperparameters, because you should only use your test set once. So you need to do this exploration, you need to do within cross-validation. And I think we're almost getting to cross-validation. I've said that we're going to get there soon. But so the other thing is marker selection that we already mentioned earlier. So now we do all these measurements, and we know that most of the proteins or most of the transcripts are not going to be related to our phenotype. So we really, it would be much better to just have build the model using the ones that we know are related, but of course we don't know which ones to start with. So we need to. So if we look at markers, so why do we do marker selection? So having few features, it makes the model easier to interpret. So one thing that we've talked about building these predictive models, and we want to predict something, but if we can also understand, that's of course a much better thing. And often when we build very complex models, we don't understand and maybe won't have a chance to understand. Few features, so it's easier to interpret. We can start thinking about biological function. They're also less likely to overfit because fewer parameters. But usually we get a little bit lower prediction accuracy. So that's something to balance. And that's what we use to then decide how many features. So as opposed to if you have many features, it's difficult to interpret. We don't know what's going on. And then, of course, more likely to overfit because we do have an enormous amount of parameters. But, of course, as we add in more and more things, we get higher prediction accuracy. But we're not sure whether that's really real.
Dr. Fenio provided a very good overview about how separating your data set in different training or test models can give a better evaluation. We also learned that when there is an increase in the degree of polynomial, the error goes down. We also learned it is better to have large data set as it will help in evaluation of the model better. Finally, we understood how to minimize the risk of overfitting of data with regularization and why we should avoid overfitting of data. We also understood two regularization strategies which can be used like ridge and lasso. In the next lecture, Dr. Fenio will talk about association and marker selection. Thank you.